everybody. I'm Aditya, who believes to be your favorite math teacher. And today I'm going to be introducing you to machines. Now, I know that you must have expected to learn about machines when you're selected, or maybe in your graduation days. But what I'm going to introduce you to today are known as mathematical machines. Now, what are these mathematical machines? We'll go there. But before we go there, let's recall what relations. So a relation was nothing but a subset of a Cartesian product between two sets. Yes, that was a relation. That was one of the relation. Yes, between two sets A and B. So let's say I have two sets A and B. Set A has three elements A, B, C, and set B has two elements D and E. So A cross B will look like how? Yes, that is correct. So that would be the relation between the elements of A and B, yes, which are known as coordinate pairs. So A related to D, A related to E, that would be another element of this set. B related to D, B related to E, C related to D, and lastly, C related to E. That is the set A cross B. Now, any subset of this set, any subset of this A cross B set would be a relation between set A and B. Yes. Now, what would be the set of all such relations? Nothing but the set of all such subsets of A cross B. What is the set of all such subsets of A cross B? That would be the power set of A cross B, right? So, power set of A cross B is nothing but the set of all relations. Let's take one more example before we move forward. Yes. So let's take a very real example of two sets, that is the set of real numbers cross the set of real numbers, which was also sometimes referred to as R2, right? So how were the elements of R2 supposed to look like? Yes, that is correct. Coordinate pair XY such that X, Y both belongs to R. Yes. Now, if I take a very specific subset of this set R cross R, let's say a subset that looks like this, which has elements like -3, 9, 3, 9, 2, 4, -2, 4, 0, 0, 9, 3 by 4, 9 by 16. Okay. Yes. Now, there would be more such, elements in this set, of course, but let's take some elements that are clearly visible. Yes. Okay. Now, this is a very specific subset of R cross R. Now, what is so specific? What is so specific and special about it? Yeah, you observed it correctly. Every y is a square of its corresponding x. Every y is a square of its corresponding x. So, if I had a machine which converted all of the such x's into its corresponding square, that would be what? That would be those mathematical machines. Yes, I know that we already have those machines. They are better known as calculators. Yeah. Okay. But not there yet. Okay. I'll not disclose the name yet. So if I have an x I will have an output y for it. Okay. And what is y? X square, right? So if I put -3 into this machine, I will get 9. If I put 3, I'll get 9 again. Okay, that is possible. If I throw in two different inputs, I may get a same output, right? But if you think about it, if you throw in the same input, can you get two different outputs? No, right? That's not possible. And keep that thought in mind. Okay, keep that thought in mind. Okay, so now these machines, okay, or these specific relations, okay, are known as what? They are known as functions. These functions are known as what? Mathematical machines. Okay, functions are very specific relations in set A cross B, where every element from set A can be related to only one element in set. Okay. Now let's take an analogy to understand it better. Let's say I have a machine that can measure heights from interval 150 centimeter to 200 centimeters. Okay. Let's consider to be the set of all heights that the machine can possibly measure. Okay. And let's consider another set A, which is a set of 3 people whose height is to be measured. Okay. Let's say the height of X is 175 centimeters. Okay. And the height of Y is also 175 meters. Let's say there's a person Z whose height is 165 centimeters. Okay. Now, the important thing to note over here is that every element from set A can be related to only one element in set B. Yes, that is the case. Every element in set A can be related to only one element in only one element. Only one element. So, yes. So now that is quite obvious also. If you think about it, that is quite obvious. Yes, a person can only have one height, right? Yes, a person can only have one height. Yes. Okay. So this is a function, right? Because every condition is satisfied over here, right? Let's take another example. Yes, let's take an example where this is not a function. Okay. Now, let's say there is a person K in set A, K for the Great Khali. Now we know that his height is more than 200 centimeters, right? So now there exists an element K which does not have a height in B. So not every element in A, not every element in A is having a height in B. Yes. So both these important keyword conditions should be satisfied. Only then it is going to be a function. Okay. Now, before we move forward, we should remember some key terms about a function. Okay. Now, there is a set of all inputs that is known as domain. Set of all inputs. Then the set of all outputs is known as what? The range of that function. Then there is a codomain, which there is the codomain, which consists of what? Which consists of the range. That means what? That means range set, better represented as f of a. Yes, f of a. Over here, a is the domain. Yes, a is the domain. Okay, a is the domain. So range set can be represented as how? F of a. Okay, considering this function to be f. Okay, considering this function to be f. Okay, now what is a codomain? Codomain is nothing but B. But what do we have to understand? This range set is contained in B. Its range set, that is f of A, is contained in B. Okay. Yes. Okay. So this is what we need to remember. Okay. Because there are certain elements in B, in the codomain. Yes. There are certain elements in the codomain which are not being linked to A, which do not have a pre-image in A. That would be the more correct term. Okay. So that is how we need to remember some terms about functions. Now, moving forward, let's take one more function, G. Okay. Now this function G has the domain to be R, and let's take domain to be Z, okay, and the codomain to be R. Okay, so this would be Z and this would be R. Okay, and this function G is better defined for all inputs X from Z to be as X square, our original specific relation in hand, right? So if I take an integer, let's say I take different integers, yeah, 0, -1, -2, 1, 2, okay? I will have an element in R which can be related to these to these elements of Z. Okay, so that would be 0, 4, and 1, right? So over here, what would be the case? -2 would and 2 would be related to 4. Yes. 1 and -1 would be related to 1. Yes. And then there would be 0, which would be related to 0, right? Yes, does this make sense? Now we know that, of course, there are some elements in R which are not being related anywhere, right? That is okay. Yes, that is okay. But what we need to remember over here is what? The thing that we need to remember over here is that every element from Z can be squared, right? Every element from the set of integers can be squared, right? So it is a function, right? And every element is only having what? One square, right? It cannot have two squares. So, of course, indeed, it is a function. Okay. So, but what would be the domain of this function? The domain of this function would be what? We have already established that. That is Z. What is the range of this function? Yes. If I have to define the range of this function, how will I define it? We define it like this. F of Z, yes, f of Z is x square such that x belongs to Z. Yes, this would be the correct definition of the range set, right? Then we have the codomain, which is already established. That is the set of real numbers. Okay. There is something that we really need to observe about these functions. What's that? That functions don't have a problem with two or more elements being linked to a common element in the codomain. Okay. For example, 2 and -2 over here are being linked to 4. Right? We saw that in the earlier case as well. X and Y both were being linked to 175. That means what? Functions don't have a problem when two or more elements of the domain have the same image, the common image in the codomain. They don't have a problem. But what if we add this condition to our functions that no element in the range set can have more than one pre-image in the domain? That means what? That every element of the range will have a unique pre-image, in the domain set. Okay. Now these type of functions have a special name. that they are known as injective functions. Now, how can I make that possible? How can I make this possible that the every element of the range set over here has only one pre-image in the O in the domain. Okay, I can make that possible by removing all the negative numbers. That is by changing my domain set. If I change my domain set to natural number union 0, then that way I will be able to make this function injective in nature, right? I will be able to make this function injective in nature. That is, the range set over here will have only one unique pre-image in the domain set, right? You can check that. Yes, 0 has 0, 2 has 4, yes, 4 has one pre-image, that's 2, 0 has one pre-image, that's 0, 1 has one pre-image, that's 1, right? Every element of the range set. So what do we have in our hands? We have an example of injective functions in our hands, where every element in the range has only one image in the domain. That is a unique pre-image in the, okay. Since it has only one unique pre-image in the domain, that's why these are known as 1-1 functions. Okay, because only one element from the domain is related to one element in the domain. Okay, that's why we call them 1-1 functions. Okay. Now, let's observe one more thing about our functions. Okay, the second important observation about our function is that our functions also do not care when they have some extra elements in the codomain, right? There are uncountably infinite many heights in this interval, yes, which do not have a pre-image in A, right? Similarly, if we check our original set, that is function g z2r g of x equals x square, we will observe that set r of real numbers also has uncountably many infinite numbers which do not have a pre-image in Z, in the domain set. Okay, so what if I don't want that to happen? Okay, what if I don't want that to happen? That means I want all of my elements in the codomain, to have a pre-image in the domain. In that case, what will happen? What will it result to? It will result to me making my whole codomain set to be the range, right? Yes. So I will have to define my codomain in such a way that it is nothing but the range x square such that x belongs to x. Okay. So B. Now this is a special type of function. Yes, this is a very special type of function. These are very special type of functions which follow this very important condition where every element of the codomain has a unique pre-image in the domain set, and they are known as surjective functions. Okay, and also we often refer to them as onto functions. Okay, so these are two important type of functions that we may see in our day-to-day life. Two broad classification of functions. Okay. Now, although these functions are mutually exclusive from each other, okay, we can combine both of their conditions. Okay, that is a function which is both 1-1 and onto as well. Okay, so these type of functions have another name. They are known as bijective function. Okay. How do I make a function bijective in nature? That is also a very important thing to understand. To do that, why don't we take a function that is already onto in nature and make it 1-1 as well? Now, for this function in particular, we have already learned how to make this 1-1. Yes, we have already done that. How do we do that? By removing all the negative values. So now my domain will be what? My domain will be nothing but the set of natural numbers union 0 element, right? So this way we will have a bijective function in our hands. Now let us try and test our knowledge with the help of a question. Now consider a function where f goes from r to x and f of x is equals 2 to the power x. Then which of the following options would be true? Now the first option says that f is 1, 1 if x is equals to r positive, that is the set of all positive real numbers union with 0. Okay. Yes. So how do we check if a function is 1, 1 or not? We check a function is 1, 1 or not if for two different values of x, the value of function is same or not. But for this function in particular, is that possible? No, right? For two different powers of 2, we are going to get different values, right? 2 to the power x1 can never be equal to 2 to the power x2. Hence, we can say that f of x1 is not equal to f of x2, right? So this function is a 1, 1 function. Now, we have one more condition over here, which says x is equal to this. Now, if you think about it, the codomain does not really matter to decide if a function is 1, 1 or not. If a function is 1, 1, it is going to remain 1, 1. Does not matter what the codomain actually is. So that's why this is going to be a 1, 1 function, and this option is correct. Now, if for the second option, if we check f is onto if x is equals to r plus union 0. Okay. Now, how do we check for any function g if it is onto or not? If g goes from a to b, the range set of g, that is g of a, should be equal to the codomain, right? That is what we have learned, right? That is when a function is onto. So let's check for our function f for all real numbers. What kind of range do we have? Yes. Now, for any value of x from the set of real numbers, this function is always going to throw a positive value, positive real number. It's going to throw a positive real number, right? And not 0. It cannot never give a 0, but our codomain is having a 0 over here. So what is the case? We check over here, our range is nothing but r positive, which is not equal to the x that we have in option B. So this option is incorrect. It's false. So false. Now let's check for third option. Now f is not 1, 1 if x is equals to r positive. No, that is not true, right? It will be 1, 1. We already have discussed that functions are 1, 1 no matter what the domain is. So this is also wrong. Now let's check the fourth option. The fourth option says f is bijective if x is equals to r positive. Now we already have established that f is 1, 1 in nature. Now what if the codomain is r positive? Yes. In that case, will our function be onto as well? Yes, that's what we checked. Yes. If x is also equal to r positive, that is our codomain is also equal to r positive, in which is the range, which is also the range of our f, right? So that means what? This means that our function is onto as well. So if a function is 1, 1 and onto both, in that case, the function is said to be bijective in nature, right? So that will be all for this video, and I will meet you in the next one where we'll be learning on how to find the inverse of bijective functions and why can we only find inverse of a bijective function. So bye-bye, have a nice day. I'll meet you in the next one.